Welcome back. In this segment, we will discuss the concept of a combination. Again, let's assume we start with a set S containing n elements. By definition, an R combination of S is simply a subset of size R, where R is an integer less than or equal to n. So, if an R combination is a subset of a set of n elements, then the order of the elements in the R combination does not matter. And that is the main distinction between an R combination and an R permutation. Remember that an R permutation is an ordered arrangement of R elements chosen from a set of size n. So in a permutation, the order matters. In a combination, the order does not matter. Again, an R combination is just a subset of size R. Now the question we're interested in is to count the number of R combinations for a given set of size n. Well, this number is denoted by CNR. Another notation that's very common is this notation, which is pronounced n choose R, which simply means you're choosing R elements out of a set of size n. So the next theorem is going to give us a formula for CNR. Again, let's assume we have a set of n distinct objects, and we have an integer r that is less than or equal to n. Then according to this theorem, CNR is equal to PNR divided by r factorial. Remember that PNR is the number of r permutations whose elements are chosen from a set of size n, which is the same n as in the number of combinations. So what that means in particular is that if you take P and R and you divide by R factorial, you get a smaller number than P and R. That should make sense. Now another way to write this fraction is to replace P and R by its formula, as we discussed in a previous segment. So here is the expression for P and R, and we just have to divide by R factorial. Now let's make three quick observations. First, what is the value of Cn, n? Well, remember, this means the number of subsets of size n taken from a set of size n. Well, the answer is 1. There's only one subset of that size. That's the whole set. Does the formula give us the right answer? Sure, if r is equal to n, then this expression becomes 0 factorial or 1, so it disappears. And r factorial becomes n factorial, so n factorial over n factorial gives you 1. The second observation is, what is the value of Cn, 0? Well, this is the number of subsets of size 0. And there's only one such subset, that's the empty set. So the answer should be 1. Let's check with the formula. If r is equal to 0, then 0 factorial goes away since that's a 1. N minus 0 factorial becomes n factorial, and those two terms cancel out to return a 1. Now the third observation is, what is the value of Cn, 1? How many subsets of size 1 do you have if you pick the elements from a set of size n? Well, the answer is n, since we have n singleton sets. So again, let's plug the value of 1 for r. 1 factorial is 1. We are left with n factorial divided by n minus 1 factorial, which simplifies to n. So again, this is not a proof of the theorem, just 3 illustrations of its use. Now, let's look at a more extensive example. Let's consider the set S equals A, B, C, D, which has an n equal 4 elements. And let's ask for the value of C4, 3. How many subsets of size 3 taken from this set of size 4? Well, applying theorem 5, we can first compute the value of P and R. So here we're asking for P4, 3. So what are all the permutations or ordered arrangements of 3 elements chosen from this set with 4 elements. But remember, we first have to choose 3 elements. So let's take the first 3, A, B, C. How many permutations of these 3 do we have? Well, the answer is these 6 permutations. Now, these are not the only possible choice for the 3 elements. Of course, we just dropped D and kept A, B, C. So what if we dropped C and kept A, B, D? Then we would have the subset A, B, D, which gives us another 6 possible permutations of these 3 elements. Now, what if we dropped the B and kept the A, C, and D? Then we would have another 6 permutations with these 3 elements. And finally, if we dropped the A and we kept the B, C, and D, we would get yet another 6 permutations. And these are all the possibilities. So if we count all of these permutations of size 3, we get a total of 24 3 permutations. And that is the value of P for 3. Notice we could have obtained this number without listing all of the permutations, simply using the previous theorem. Remember that P for 3 is equal to factorial 4 divided by factorial n minus 3, or 1 factorial. And of course 4 factorial is 24. Now remember, what we are looking for is the number of combinations, that is the number of subsets of size 3. So we listed all of the permutations here, and that should allow you to realize that, for example, these 6 permutations are just reorderings of the same 3 elements, A, B, and C. And since in a set the order doesn't matter, these 6 permutations correspond to a single subset, namely A, B, C. And similarly, those 6 permutations corresponds to the one subset A, B, D. These 6 permutations are permutations of the same subset A, C, D. And finally, these last 6 permutations are permutations of the set B, C, D. So what we conclude is that there are only 4 subsets of size 3. In other words, the value of C for 3 should be equal to 4. So we can check that by applying the formula in theorem 5. So we get P for 3 divided by 3 factorial. We already know that P for 3 is equal to 24. 3 factorial is 6. So we get 24 divided by 6, or 4. So the reason theorem 5 holds is because when we count the number of permutations, we get the same subset repeated many times. How many times? Well, since the subset is size 3 and the total number of permutations is 3 factorial, that's why we have to divide by 3 factorial to eliminate the redundant arrangements. And in general, when the size of the subset is R and we count all of the permutations, we need to divide by R factorial to get rid of all the duplicates for the same subset. Let's look at one more example, which is a modification of the previous example with the UWO teachers. So let's say you were to cast a ballot for the best 3 teachers at UWO. Now here we're not looking at ranking the 3 teachers or ordering them according to some property. We just want you to vote for the top 3 teachers in any order. How many distinct ballots would you have to choose from in this case? Well, since the order of the top 3 teachers does not matter, what you're really doing is you're really choosing a subset of size 3 out of the set of 800 teachers. So the answer to this question is simply 800 choose 3, or in other words, C 800, 3. Now, using theorem 5, we can compute factorial 800 divided by factorial 797 That gives us 800 times 799 times 798. And let's not forget to divide by r factorial, which in this case is 3 factorial, or 6. And the final result is approximately $85 million for this example. Now let's conclude this segment by stating and proving a theorem that can prove quite useful when counting r combinations. Theorem 6 states that given two integers r and n, such that n is greater than or equal to r and both integers are non-negatives, then the number cn, r is equal to the number cn, n minus r. Proving this theorem is pretty easy. We're going to start from the right-hand side of this equality, and then we're simply going to use the formula from theorem 5. So remember, cn, n minus r is just n factorial divided by n minus r factorial, and another factor in the denominator is going to be n minus r, the whole thing, factorial. Again, make sure you understand this application of theorem 5. Now from here we can just simplify this factorial. N minus n is equal to 0, so that disappears. Minus r equals r, so we are left with this simpler fraction. Notice in the denominator we have a product of two terms, so we can simply switch the order of these two terms to get this new fraction, and this fraction is nothing but CNR. And this concludes the proof of our theorem.